Welcome to this section on corrective measures. In this section, we shall look at embeddings and transfer learning, then also other existing architectures which we could use to obtain better results. Let's go ahead and see what embeddings are all about. Supposing we have a vocabulary of words made of just two words, read and pullover, and the one hot representation of the word read will simply be this one hot vector with all zeros and 1 at the very first position. Then for pullover, we have all zeros and 1 at the second position, which happens to be the last position because our vocabulary is made of just two words. Now, if we're given an input, say read pullover, combining these two gives us this matrix. And since our vocab size is of 2, we could represent this in a two-dimensional vector space. In this 2D plot, we have the first point, 0, 1, which is this, and the next point, 1, 0. So this is the pullover in this vector space, and the word read, here is it in this vector space. Let's now go ahead and increase our vocabulary size to 3. So now we have read, pullover, and Monday. Now read can be written as, or can be given in the one hot notation as 1, 0, 0, then pullover 1, or rather 0, 1, 0. Now combining these two, or not actually combining these two, but if we have a sentence with the two words read pullover, so we want to input this into a model. We have read pullover. What gets into our model is 1, 0, 0, that's read, and then pullover 0, 1, 0. In our vector space, we could plot this out. Now we see that we leave from a 2D to a 3-dimensional vector space because our vocabulary size is of 3. So plotting this out, we have read and then pullover. So here we have the point 1, 0, 0, and then the point 0, 1, 0. So there we go. Now we have the same 3 vocabulary size, or 3 words in our vocabulary. Then we want to look at this word in a vector space, or rather the sentence Monday read pullover. We see that it becomes 0, 0, 1. So Monday is 0, 0, 1. Then read is 1, 0, 0, as we've seen here. Pullover is 0, 1, 0. Plotting this in our vector space, we have Monday, we have read, and then we have pullover. Now the problem with the way of representing that we've been working with so far is that as we increase this vocabulary size, we have this matrix which becomes very large. So if our vocabulary size is, say, 100,000, this is going to be a 100,000 by 2 matrix. Since for the word read, for example, we're going to have 100,000 hot vector, or a one hot vector with 100,000 different positions, and then pullover we're going to have 0, 1, 0, and then 99,997 other zeros to form a 100,000 vector, or rather 100,000 dimensional vector. And apart from passing in this kind of large matrices into our models, this data in this form is very sparse. As we could see from these different plots, we see that this read, pullover, and say Monday do not translate any other extra information apart from the fact that they are just tokens which are getting into a model. So what if we could modify this way of representing our data such that the words read and pullover will be more related as compared to the words Monday and read? And that's very clear because Monday and read wouldn't have, or actually don't have, much relation as compared to the word read and pullover. And in many sentences, or many times, we are going to use the words read and pullover, many more times or far many more times as compared to when we use the words Monday and red. And that said, there is this idea of the embeddings. Now, what does this mean? This simply means that instead of representing all these words as one hot vectors that we see here, we could represent them as float vectors but in a lower dimension. So we have red pullover Monday can now be represented as say 1.2, 0.3, 0.45, 0.77, 0.5, 0.8. Now this red, instead of being 0, or rather this Monday, instead of being 001, is now represented as 1.2, 0.3. Then the red, instead of being 100, is now represented as 0.45, 0.77. Then pullover, instead of being 010, is now represented as 0.5, 0.8. So plotting this, we'll find that we are no more in a three-dimensional space, but now instead in a two-dimensional space. So we've reduced the dimensional space to a 2D dimensional space. Now let's plot this out. We have Monday, we have red, and then we have pullover. We'll see clearly from here that instead of just having this in their different positions as this orthonormal vectors, what we now have is this vector, or these vectors Monday and red, which appear to be very close to each other as compared to say Monday and pullover. And also notice how red and pullover are closer to each other as compared to Monday and pullover. So although neural networks have that capacity to learn from very large data sets and help us do predictions based on these large data sets, it's important that we modify these data sets such that before passing them to the model, they are in a form in which the model can learn even more quickly and more efficiently from this data. We can see clearly from here that the word Monday red pullover represented as this, and the word red Monday red pullover represented as this can have two different effects on our model. As with this, the model already sees that these two are closely related and can take certain decisions based on this fact, and also can learn from this data even quickly. Now that said, in the case where we have, let's say, the words red pullover, you'll see that this could be changed or modified such that instead of having 100, we now have A11, A21 for red, and then instead of having 010, we modify this to have A12, A22. So we'll leave from 3D to 2D. Also note that we could leave from 3D to 1D. Note that high quality embeddings have to be in such a way that certain relations like say football and sports with dog animal could be clearly seen. This means that if we are in a lower dimensional space, the distance between the vectors representing the position of football and sports, so this distance should be approximately similar to the distance representing the words dog and animal, as football is a type of sport and dog is a type of animal. Another example of a relationship high quality embeddings should be able to show us is, for example, the fact that friend and friends, that's this pair friends, is related to the pair girls. So this means that in the vector space, the distance between friend and friends should be similar to the distance between girl and girls, as here we have the singular, plural, singular, plural. Then so the example where we have antonyms, we have the distance between love and hate should be similar to the distance between fast and slow. You could check on our linear algebra course to get a deep understanding on vector spaces. In a vector space, if we have two vectors u and v, now talking about vectors are basically these points that we have here, and their magnitude is with respect to the origin. So if we have, say, this point 0.45, 0.77, this is the actual vector which links the origin and itself. So given that the origin is the point of coordinate 0, 0, we could just say the vector is this. Now that said, if we have to find the dot product of two vectors u and v, we have is the same as u transpose times v, which is the same as the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors u and v, which we call here theta. Now, finding cos theta, we have uv, that's u dot v, the dot product, divided by the magnitude of u times the magnitude of v. And this is known as the cosine similarity between two vectors u and v. It's also one of the most popular ways in which scientists compare two vectors in this kind of embedding space. So this means if you want to compare these two, we would have this vector dot this, that's the dot product of this vector and this vector, divided by the magnitude of this times the magnitude of this. And so here, instead of computing this distance, we could replace this distance by the cosine similarity. And that said, the cosine similarity of, say, love and hate should be similar to the cosine similarity of fast and slow. Let's now see how we obtain this embeddings from this one hot vector. Suppose we have this word again, Monday red pullover, as input I. We've seen the representation right here. It's of dimension L, or of shape L by V, where L represents the sequence length and V the vocabulary size. Notice that this matrix here isn't exactly the same as this matrix, as this is the transpose of this matrix. The reason why we transpose this is because here we are having to represent it as the sequence length by the vocabulary size, whereas here it was represented as the vocabulary size by the sequence length. Now that said, in our example here, our sequence length is considered to be L. In this case, it's actually 3, so it's a 3 by 3 matrix, and our vocabulary size is 3. But we shall maintain this L so that you could see clearly how these embeddings are gotten. Now, once we have this, we can define an embedding matrix such that the number of rows is the same as the vocabulary size of our defined vocabulary. So in this case, our vocabulary size is 3. That's why we have 1, 2, 3 rows, and the number of columns will be the same as this new lower dimensional space, or better still, the size of this new lower dimensional space. In this case, where our lower dimensional space is of size 2, of dimension 2, we're gonna have this E equals 2. So if you look at this carefully, we are defining a matrix which could translate from this vocabulary size, or from this 3-dimensional space, to a 2-dimensional space, such that once we multiply our input by that embedding matrix, we're gonna have an output of shape L by E, because multiplying a matrix of dimension or shape L by 3 with this matrix of shape 3 by 2, we have L times 3, or L3 times 3 times 3 by 2. It gives us L by 2, which is L by E, or L by V times V by E. It gives us L by E, which, as we've seen, is dimension 3 by 2. And so we have our 3 inputs, or we have all the 3 parts of our sequence length still maintained. Our sequence length doesn't change, and that's normal because we have 3 inputs: Monday red pullover. So we still have Monday red pullover, but with the difference that instead of having 3 vectors or 3 numbers in this vector which represents Monday, we now have just 2 numbers. Here, instead of having this 3, we now have just 2. Instead of having just 3, we now have just 2. And this is thanks to the fact that we've multiplied this with the embedding matrix. Now let's look at this more generally. Supposing we have a vocabulary of size 100,000. So we go from A is the of width up to the 100,000th word in the vocabulary, which we could say is pulverize. In that case, if we want to represent or if we want to pass this word, this sentence, which is made of a group of friends met today, that is 1, 2, 3, 4, 5, 6 words. In that case, previously we'll have a one-hot representation where we have 6 different positions. This A, this is group, this is of, this is friends, met today. And now for A, since A is the first or occupies the first position in our vocabulary, we have 1 and the rest zeros. Now the next is group. We have 0 for the first position, 1 will be found somewhere in the middle, and then up to the rest we have all zeros. Then of, the same, friends the same, met the same, and today the same. So in that case, we're gonna have this 6 by 100,000 dimensional matrix, which is not only large but very sparse. Now that we have this, we could define an embedding matrix E of dimension, the vocabulary size of this, which is 100,000, by a lower dimensional embedding size, which we've chosen to be 300. So we're living from 100,000 to 300. In that case, multiplying I by E will give us LV by VE, LE. So we're gonna have L by E. In that case, since E is 300, we're gonna have 6 by 300. And so now this input, which was initially a 6 by 100,000 matrix, is now a 6 by 300 matrix. So not only this is more efficient computation wise, we are now also able to represent this data in a way in which our model can learn better from it and also faster from it. Including an embedding layer in your code is also very easy. After the inputs, you could simply have this embedding right here, which is defined such that we take in the vocabulary size and then we output the embedding dimension. So if the vocabulary size is say 100,000 and the embedding dim is 100, simply we're living from 100,000 to 100 dimensional space. Once this is defined, as we've seen already, we include in the code, and that's fine. From here we could see that the number of parameters equals simply the product of the vocab size and the embedding dimension. In our case, we have a vocab size of 2000 and an embedding dimension of 100. That's why this layer here has a number of parameters equals 200,000.